A very good morning to one and all. We are all connected to each other, biologically to the earth, chemically to the rest of the universe, automatically. A very good morning to one and all. On behalf of the management of JMJ College Tenali, myself, Aksha CH, lecturer in Department of Botany, welcome you all to this 5-day international webinar on current trends and future advances in life science and chemical sciences.
Good morning, ma'am.
Let us commence our webinar with a prayer song, seeking God's divine blessings.
As the world wakes up in the morning and the sun smiles with its warmth, the birds spread their wings as they soar the vast blue skies. The flowers give off their scents, fragrance fills the air. Oh, this earth is a paradise so delightful to behold. How can we be so unkind to this planet where we live? This God's gift to humanity, let not ruin make its way. As the waters in the rivers flow into the roaring rapids, all the trees sway and dance with the rhythm of the blowing wind. As the rains drench the ground, the whole creation breathes with life. Oh, this earth is a paradise so delightful to behold. How can we be so unkind to this planet where we live? This God's gift to humanity, let not ruin make its way. All the mountains and the hills are crowned and cold.
Before we commence the session, I would like to give you a few instructions. Dear participants, please mute your audio and switch off your video throughout the webinar to avoid inconvenience. If you have any questions during the presentation, please type them in the chat box in your control panel. We will respond to your queries after the session. Thank you for your kind cooperation. Now I request Kirtana Madam to welcome the resource person. Madam, please introduce our resource person.
Thank you, Anujya ma'am. It's my pleasure to invite today's resource person, Dr. Prashant K. Padduturi. Sir has received graduation in the year 1995 from Usmania University, India. Sir obtained post-graduation in the year 1998 from School of Chemistry, University of Hyderabad, India, and Sir obtained his PhD from the Department of Inorganic Chemistry, School of Chemistry, University of Hyderabad, India, in the year 2005. Sir qualified GATE in the year 1998. During doctoral program, Sir worked as CSIR UGC NET Junior Research Fellow from 1919 to 2001 and Senior Research Fellow from 2001 to 2004. After completing his doctoral degree in the year area of inorganic chemistry, Sar worked as postdoctoral fellow at Department of Chemistry, Brock University, Canada, from 2005 to 2011. Later in the year 2013, he joined as assistant professor in the Department of Chemistry, UPEI. Further, in the year of 2014, he joined as research associate in the Department of Chemistry, Brock University, Canada. And now Sar is working as assistant professor in the Department of Chemistry, Biouniversity, University of Minnesota, Duluth, US. Sar is one of the leading resource persons in the world of research and consultancy. Sar holds his research degree in inorganic chemistry. Sar has guided several research scholars for PhD program. His main research interests include inorganic chemistry. He published a number of research publications in various national and international journals with scientific reputation. He is currently serving as potential reviewer for various Scopus and SCI journals. Sar visited as guest faculty of various reputed universities and colleges. Sar delivered a number of invited lectures, talks, keynotes, addresses at different seminars and conferences. Thank you, sir. Now I hand out the session to today's resource person, Dr. Prashant K. Poduturi, sir. Sir, please carry on, sir.
Okay, thank you, Kirtana, for a nice introduction. Can you hear me, guys?
Yes, sir.
Yes, sir.
Okay, thank you. Okay, first of all, I would like to thank webinar organizing committee for giving me this wonderful opportunity, and also I would like to congratulate JMJ College for organizing such a wonderful webinar. Let me share my slides. Entire screen.
So just please go to present.
Yeah. Actually, I'm trying to share my screen, but it's not allowing me.
Just take your entire screen.
What is that?
Go to present and there select your entire screen. Then only you can present your PPTs also. Sir. Just
Cannot
take
share.
your share. Go to share.
Yeah, sure. Yes.
The square button which is the up arrow. Up arrow. There you select your entire screen.
So a window, right?
Not a window. Your entire screen.
Yeah, I'm doing that, and
There you select the window. Share your entire screen. Pop
yeah.
down your.
Share. Well, I think I need to change something in my computer system settings. Okay, let me check that quickly.
Otherwise, can you send the presentation to us, sir? For my side, I can present.
Hold on, just I
Just
think I should.
mail it, sir.
Okay, I'll do that.
మెయిల్ పంపిస్తారు చూడండి సార్. ఓకే సార్, ఓకే సార్, అంతే సార్. అనుకుంటా.
సార్ మ్యాక్సిమైజ్ స్క్రీన్ అవసరం లేదా?
ఓకే సార్, ఓకే సార్.
మ్యాక్సిమైజ్ చేయాలి. ఓకే ఓకే.
Sir, just please change the slides, sir. Whether it is working or not, we will check. Okay, sir, it's clear. Sir, your voice is not audible, sir. We can't hear your voice, your audio. I think you muted your side, sir. Yeah.
Now.
Okay, sir. Okay.
And video.
Now it's audible.
Now you can see me, right?
Yes, sir.
All right. Hopefully everything is set. Okay. So today, I think I'm gonna talk about my research that I've been doing from last several years. So I mean, by training, I'm a porphyrin chemist. I'm going to show what is meant by porphyrin in a minute. But before getting into details, I would like to thank these people. Without these people, this work wouldn't have been possible. This is my research group. The work today I'm presenting. Most of the work is done by these students, and funding for these different funding agencies. And I do have a lot of collaborations, and my collaborators contribute different studies for my research. And this is the just a recent group picture. We took it in summertime. All right. Okay. So what we do, this is the molecule we deal with in my lab. It's called porphyrin, and you can see that it's a very big molecule and a highly conjugated molecule. And as you can see, I label this name with different colors. That means these compounds comes into different colors. And they have a very impressive properties, and also these molecules are, I would say, versatile molecules. The reason I want to say that, we all know that in a plants, plants do the photosynthesis, right? In photosynthesis there is a chlorophyll molecule. For plants, the green color comes from the chlorophyll molecule, right? That's the chlorophyll molecule, and you can see that its backbone is very similar to the porphyrin structures. So I would say these two are actually from the same class. In chlorophyll, if you notice, at the center there is a magnesium, right? So there is a magnesium metal. If there is a magnesium, this molecule acts like a chlorophyll. It's collect the sunlight energy and use that energy to produce chemical fuels, like for example carbohydrate, right? And now what you can do, you can just change the central element magnesium to iron, right? So there is iron here, and then change some functional groups on the periphery. Now all of a sudden it becomes heme, right? And heme now, it has a very different applications in our body. So this molecule now act like a oxygen transporter in our body, right? And you can see that by simply changing the central element and also some minor peripheral functionalities, you could change completely its properties. That's why I call it a versatile molecule. And because of this versatile property, porphyrins are useful in many applications. So in my lab, we focus on these three different research areas. One is the artificial photosynthesis. From the name, you can understand what is meant by artificial photosynthesis. It's basically mimicking the natural photosynthesis. So by doing so, what we are trying to do, we are trying to convert sunlight energy into solar fields. Okay. And then the second project we work on, it's called molecular machines or molecular electronics. So here we are trying to develop like a tiny molecular machines. The idea is that convert sunlight energy into mechanical energy. Okay, so I'm going to talk about that later. And the last one, we also work on something called photodynamic therapy, which is completely different from the first two. Here we use a light plus a drug, and the aim is that to kill the cancers in the body. Okay, so those are the three research topics we work on in my research group. All right, so I want to actually just give a little bit about like a brief introduction about porphyrins. So this is the porphyrin structure, and I just want to highlight these different positions. This is called the meso position, and these are called axial positions, and this is called beta pyrrolic. Okay, so we're going to use in the next coming slides. You're going to see that how we are using these functional positions to change the properties of these molecules. Okay. So these molecules are absorbed strongly in the visible region, right? Because if you look at chlorophyll, right, chlorophyll absorb the visible light. So that's how it, the sunlight energy is converted into chemical energy. And the easy to tune the optical and redox properties. So means we can change the properties of these molecules very easily by changing R group here, or by changing M group, or by changing this X group here. So easy to functionalize, and they have a high fluorescent quantum yields and long-lived excited state. So in this talk, mostly I'm going to talk about porphyrins, which contains the main group element. So main group means, I think if you know the periodic table, the upper right corner elements are considered main group elements. So I'm going to deal with only these particular porphyrins because they have very some unique properties. So I'm going to just give an example why main group porphyrins are special, or they are unique. If you look at these three porphyrins, right? So the backbone is exactly same. Backbone means the porphyrin structure is exactly same. Only the difference is that here you have aluminum, and there is a tin, and there is a phosphorus, right? So when you have aluminum, these are the something called electrochemistry. So what I'm showing here, these are the oxidation potentials and reduction potential. Oxidation reduction means basically, when we say oxidation means, potential is required to remove the electron from the molecule. So we measure that using the electrochemistry. Okay. So when I say reduction potentials means, when you can add a electron to the molecules. Okay. So you can add, this is the one electron you can add. You can also second electron. So we are basically measuring how easy to add electron, and also how easy to take off the electron from the molecule, right? So when you have aluminum, so the oxidation is going to be 1.20, and these are the two reduction peaks, okay? But if you replace aluminum with tin, right? And all of a sudden your oxidation becomes 1.40, and you can see the reductions are shifting to the like a positive side. And then if you replace the tin with the phosphorus, it becomes actually even much higher. It's going to become 2, right? And then the reduction becomes very easy, right? So the way you should read these numbers, when you have a 2 O's almost, this means it's very hard to oxidize. In other words, it's very hard to remove the electron from the molecule. And then when you look at these reductions, they have a like a low negative values, means it's easy to add electrons to these molecules, right? And this example clearly shows that how easy to change these properties by simply changing this central element, right? Aluminum to tin, tin to phosphorus. So that's why we mostly concentrate our research on the main group porphyrin, because they have these unique properties, and these unique properties actually make them suitable for different applications that I mentioned earlier. Okay, so what I'm going to do now, I'm going to actually show some series of porphyrins, and I'm going to show their properties. After that, I'm going to talk about their uses in different applications. So let's start with aluminum porphyrin here. So again, this is how we make a porphyrins in my lab. We always start with a it's a precursor molecule. These are the aldehyde molecule corresponding. R's are, these are different R's, or aldehyde plus pyrrole, and you get this porphyrin molecule. Initially, you can see that there is a the inside cavity is empty. There is nothing inside. So you could insert in this one any type of elements. It could be non-metal or metal. Right. In this case, I'm inserting the aluminum. So you get aluminum. So this is aluminum porphyrin. When you have aluminum, this porphyrin comes with this axial hydroxy. Okay? So this axial hydroxy is very reactive functional group. You could attach, for example, benzoic acid. You can make this molecule, right? And just note that here R is all these different substitutions, like 5 different substitutions. So we prepared this series of porphyrins with aluminum, and then we look at their properties, how they behave in terms of optically and electrochemically. So when I say optically, means we mostly focus on absorption spectroscopy and fluorescence spectroscopy, right? So this is just absorption spectroscopy on the left hand side. And you can see that on the y-axis, this is the, this wavelength is entirely, it's a visible range. Means, these porphyrins are very good light absorbers in visible light, which is the actually fundamental requirement for the, the 3 applications I mentioned at the beginning of the talk. And then, this is the electrochemistry. Again, when we, like, for example, when we want to, mimic the, or when we want to construct the artificial photosynthesis, one thing we always look at that, how easy to add electron and how easy to remove the electron from the molecule, right? So therefore, so the electrochemistry becomes, essential for, these studies. So you can see that. So these are the, this positive side is the oxidation potentials, means, you're removing electron from the molecule, and this, the negative means it's you're adding electron to the molecule. Okay, so these numbers actually makes, these numbers actually useful to explain the, the optical properties of the design molecule in the study. Okay, if we just kind of, I just summarized all those values here. This is the absorption data, and this is the, reduction or electrochemistry data. I just want to point out something here. If you look at, this porphyrin and this one, right? So this has a, this has a just a, phenyl substitution, right? And if I go back here, so that, porphyrin is with, I'm comparing with this one with this porphyrin, right? So when you have just a phenyl, oxidation is 1.22 and reduction is negative 0.86, right? But if you substitute with a pentafluorophenyl, then all of a sudden its potential becomes oxidation becomes very high. Means it's not easy to oxidize, but it is easy to reduce, right? So these numbers clearly tells me that this porphyrin could be very it could be a good electron donor, means you could easily remove electron, and this porphyrin could be very good electron acceptor, means you can add electron very easily. Okay, so again, these numbers are actually makes very important concept for our studies. Okay, and then another thing is that aluminum porphyrin. This is aluminum porphyrin, right? I just showed that. So this has a other unique property that if you probably in your undergraduate chemistry or inorganic chemistry, you may be learning about Lewis acid, Lewis base, Lewis acid, Lewis bases. So here, aluminum act like a Lewis acid. Okay, means if you add a Lewis base, for example, this imidazole unit is gonna bind aluminum through the Lewis acid base interaction, and you can make this type of complex. Okay, so aluminum has a this slide explains that you could attach two different things to the aluminum porphyrin, right? This is one thing, one type of substitution. This is the second type of substitution. So aluminum can have these two different type of substitution at the same time. Yeah. So this property we will use in the upcoming in the coming slides. Okay. But anyway, so you can monitor the this complex formation by using the absorption titrations. Okay. And these are fluorescence titrations. Okay, so that's the one type of aluminum, one type of porphyrins, which is aluminum porphyrins. Now I'm going to show the another type of porphyrin molecule. So here again, we made this porphyrin, and you can see that there is a cavity is empty. There is nothing in the cavity, right? And now we have R here. R are actually these four different substitutions. Okay. And then we inserted the, this time antimony. Sb is antimony, again, is one of the main group elements. And you have initially it as a chloride, and then we reacted this with methanol. You get this methoxy substitutions, right? And so we made this four molecules with these four different substitutions, and you can see that these are the crystal structure for each of those. So when we made this molecule, we thought that this is just a typical porphyrin series with we were actually not expecting any unusual results from this series. But when we started measuring the the optical studies, means just simple absorption spectroscopy, right? You can see that. So again, they absorb the light in the visible region, right? But most importantly, so you can see the red one means when R is a phenyl, that's a sharp band there, right? But if you if you, instead of this one, now if you have a paramethoxyphenyl, this sharp band becomes broad, it becomes small, right? And then this dimethoxyphenyl, that's even become broad, and then trimethoxy is actually the has a maximum broadness in the absorption profile. Okay, so these results clearly shows that the series that we prepared is actually it's not ordinary porphyrin series. It has some kind of a interesting results. And then we measure their electrochemistry. Again, we are looking at their oxidation reduction potentials. I just summarize those results here. Right, if you these numbers, right, you can see all these porphyrins have a very low negative values. Means these porphyrins are easy to reduce. Means you can add two electrons, like one electron and the second electron very easily, but they are very hard to oxidize. Which means these porphyrins could act like a very good electron acceptors. All right. And to explain, the broadness, basically, what is causing this broadness. What we did, we we took actually the DFT, which is a computational studies. So what you're looking at here, it's basically it's called ESP maps, means electrostatic potential maps. Potential maps means it's actually these maps shows that the electron density on the surface of the porphyrin. Okay, so what you have to know here, blue means, when you see blue color, blue means it's electron poor region, means electron deficient region, and red means electron donor or high electron density region. Okay, and if you look at start from here, right? So we have phenyl groups here. When you have phenyl, there is a little bit of red color on the peripheral, and there is a blue color at the center. Okay, and now if you have a paramethoxy, so the red colors started increasing, right? And the blue color is still in the center, and dimethoxy is more red color, blue color at the center, and trimethoxy is the highest red color on the peripherals, and there is a blue color, right? So what this map shows that you have a molecule. So within the molecule, you have two different regions. One region is the electron-rich region, and one region is the electron-poor region, right? Within the same molecule. So when you have such a condition in a molecule, it's always possible that you going to have something called charge transfer character or charge transfer property. Means charge transfer property means is nothing but basically electron density transfer from the electron rich region to the electron poor region. So that's what we define as a charge transfer property in the molecule. Okay, so this charge transfer property basically has a interesting implications on the optical and also electronic properties of the molecules. So from these studies, we know that, from the absorption studies, okay, right? And now we can explain this broadness by using this charge transfer property. Because of the charge transfer property, there is a, what do you call, a modulation of the electronic structure in the porphyrin, and that's why, it's causing this broadness here. Okay. And then, if you look at their, the something called frontier orbital, again, maybe, you're learning or you learned about the HOMO LUMOs, right? These are HOMO means highest occupied molecular orbital. LUMO means lowest unoccupied molecular orbitals, right? And if you look at carefully, right? So LUMO, right? This is these are the orbitals. The orbitals are in 4 molecules. These are the 4 different molecules. The LUMO is completely localized. The center of the the porphyrin ring, right? Right. But if you look at the HOMO, so HOMO initially on the ring, and then as you increase the methoxy groups on the phenyl, there is a methoxy here, and then you can see that the HOMO is slowly started shifting to the peripherals, right? So here it's mostly on the peripheral, and here, right? So you can see that HOMO initially was here, but slowly shifting to the peripherals as you put more methoxys. Okay, again, these all results actually, kind of supports the, the charge transfer property in these molecules. But the ultimate, the evidence come from something called solenotochromism. Solenotochromism means if you have a charge transfer property in your molecule, so this charge transfer property is going to be strongly solvent polarity dependent. Means it depends on the solvent polarity. Okay, so what we're doing here, we took a 4, 1, 2, 3, 4, those 4 samples. Okay, and we measured the their fluorescence under the ambient light, also under this UV light. So this is the something it's called acetonitrile, which is the strong like a polar solvent. In a polar solvent, you can clearly see that 1, 2, the compound 1, compound 2 are strongly fluorescent. Right? Okay. Compound 3 and compound 4 are completely non-fluorescent. Right? And then if you lower the polarity from acetonitrile to something called dichloromethane, it's a lower polarity solvent than acetonitrile. And now you can see that the fluorescence is recovering for compound 3, right? And then the fluorescence from 4 is still not observed. And then if you go to toluene, which is the actually non-polar solvent, so it's still 1, 2, 3 are fluorous, but 4 is still non-fluorous. But if you go for benzene, again, it's a slight, it's a non-polar solvent. You can see that, the compound 4 is started fluorous. Okay? So this study clearly establishes that we have a charge transfer property in this antimony porphyrin series. Okay. All right. So that, I think I'm going to skip that. Anyway, so that's the, antimony series. So what we learned from antimony, so antimony series has a charge transfer property, and also antimony porphyrins can act they can act as a very strong electron acceptors. And then after that, what we did, we thought, okay, because if you remember, the antimony belongs to the group 15 of the periodic table. So just above the antimony, we have a phosphorus in the same group. So we thought, okay, let's put phosphorus in these porphyrins. What happens? So again, we started with this porphyrin, right? This time we have a 5 different porphyrins. So we added this extra one. So the difference between 4th and 5 is that, so this is the 3,4,5 trimethoxy, and this is a 2,4,6 trimethoxy. So they have the same number of methoxy group, but their positions are different. Okay. And so we inserted the phosphorus here, and then reaction with the methanol, getting this methoxy phosphorus porphyrins. Okay. And you can see the crystal structures of these porphyrins. So again, if you look at the cytochromism, I mean, what you can expect, from the previous antimony series, if you have a 3 methoxys, we had a very strong charge transfer property, right? So you could expect the same behavior from the series, because this also has the 3 methoxys, and this also 3 methoxys, right? So we expect, charge transfer in, porphyrin 4 as well as porphyrin 5. But if you look at the, cytochromism experiment, again, this is the polar solvent, right? So 4 is showing strongly charge transfer character, but 5 is not showing any charge transfer character, even though it has the same number of methoxy groups. Okay, and DCM, so the fluorescence is coming back, and the toluene, right? So again, these studies establish that we have a charge transfer property. Okay, but also these studies, additionally, prove that, here the number of not only the number of methoxy groups, but their position also important. So when they are in actually 3, 4, 5 positions, they are able to induce the charge transfer property. But when they are 2, 4, 6 position, they are unable to induce the charge transfer property in this series. Okay, so that's what actually unique about this phosphorus series. And then I think I'm going to skip this too. Okay, so this is another again ESP maps. Again, you see the blue. If you monitor the blue color and red color, right? You can see red color we have initially when you have a just a phenyl, you have a kind of a lighter color on the peripherals, and the blue color at the center. As you put a methoxys, right? So the red color increases on the peripheral, right? And this is the 3,4,5 trimethoxy, and this is the 2,4,6 trimethoxy. If you focus only on the number 4 and number 5, right? So in number 4, you can clearly see that there is some blue color and red color on the peripheral. So which means again you have a 2 different regions in the same molecules. Therefore, charge transfer is possible. Okay, but if you go for the 5, you can see that there is no blue color at all. It's completely red color. Means there is no electron pool region So when there is no electron poor region, you can't have a charge transfer property in this molecule. So that's what actually this supports. And so this is the again another series, right? So we talked about aluminum porphyrins, antimony, and the phosphorus, and now I'm going to show the bismuth. So bismuth is actually again same group 15. It's below the antimony. So here what we did, we took a porphyrin. Again, R is all these different positions, different functional groups. Okay? And now cavity is empty. You insert the bismuth. There is a bismuth now. Okay? Right. So these are all the different functional groups we are using as a R. Okay? And again, just kind of show you that what we did here, we are actually we selected these functional group in a way that you can see this is trimethoxy phenyl, which means is a as you know that from your organic chemistry. So the methoxy groups are electron donating groups, right? So when you have methoxy, this is going to be electron rich group. Okay, and then if you go here, fluorine, right? If you look at your periodic trends, right? Fluorine is the I think fluorine is the highest electronegative atom in the periodic table, which means it withdraw the electron density from the phenyl. Therefore, this group becomes electron poor. So we gone from the electron rich unit to this way to the electron poor substitution. Okay, and then we monitor the properties of the bismuth as a function of these R groups. So what I want to show here, actually just want to show the absorption spectrum. So this is the typical absorption spectrum, right? So again, these porphyrins are absorbing the visible light, which is the fundamental requirement for my research. And most interestingly, again, you probably heard about fluorescence and phosphorescence, right? So these porphyrins actually, if you look at this spectrum or spectra, so we have these two bands, right? So these are coming from the fluorescence, fluorescence process, and this is coming from the phosphorescence process. Okay? And it's called dual emission. This is a very rare case. Usually molecules will not emit, like it will not show phosphorescence and fluorescence at the same time. Generally, phosphorescence is only visible at very low temperature. For example, the liquid nitrogen, which is 77 kelvins. So if you freeze your sample at that temperature, usually samples show the phosphorescence. But here, so this bismuth series actually showing phosphorescence at room temperature again. So this is again very interesting results. We just got it. Okay. So anyway, that's the the bismuth series. All right. So that's the I mentioned 4 different porphyrin series. Now I'm going to show how we are using these porphyrins for different applications in the lab. So I'm going to start with artificial photosynthesis. As you recall, I mentioned that artificial photosynthesis means it's basically so mimicking the natural process, right, or mimicking the plants. Whatever the plants are doing, we want to do that in the lab by using artificial compounds. Okay, so the question is that why we need to worry about solar fields or why we need to worry about artificial photosynthesis? Well, so again, I'm kind of showing this pictorial diagram here. So this is us, right? This smiley face. These are the humans, right? So if you want to keep ourselves happy, we need to keep our planet also happy, because our well-being is completely dependent on our planet. If we keep our planet happy, we're going to be happy. But right now, actually, we are doing the other way. We are troubling our planet by emitting lots of greenhouse gases, right, by burning the fossil fuels. So when I say fossil fuels, it includes natural gas, in India we call petrol, right, and coal, right? By burning these three things, we are producing, almost lots of carbon dioxide. So, this picture actually shows that how much actually we're burning. So this is the total energy consumption. Out of total energy consumption, this is, oil and coal and the gas, right? So almost like, close to 90%, is coming from these fossil fuels. Only like, less than 10% is coming from the renewables or hydro or nuclear, right? You can see, the green is only 2% is actually come from the renewable, for example, like a solar panels and so on, right? So, as we burn this much fossil fuels, we produce, lots of carbon dioxide. Every year we release almost like 20 billion tons of carbon dioxide every year. Okay, of course, half of this carbon dioxide will be used in natural processes such as photosynthesis, right? That plants convert carbon dioxide into carbohydrates, right? So only half of them will be consumed, but half remains in the atmosphere. Okay, and we are adding this one every year, right? So this is kind of building up in our atmosphere, and it is causing global warming, and also it is affecting the human health. So therefore, these are some simple justification. I'm telling you why we should go for the solar fuels. Okay, but how to convert the how to get the solar fuels? Well, so nature shows this conversion in the plants, right? So plants convert sunlight energy into carbohydrates, right? So this is what exactly we have to do in artificial systems. But in order to do that, first of all, we need to understand what exactly happens in natural photosynthesis, right? So just want to briefly explain what happens in photosynthesis. This is your plant. Okay, it's kind of a leaf, represent a plant. Again, just remember that this is the oversimplified diagram. Photosynthesis is not this simple. It's a very, very complex process. But this picture actually enough to explain our purpose. So these circles represents is a chlorophyll molecule. Again, as I mentioned, this is a magnesium there. That's kind of a porphyrin derivative, right? So these circles, they act like an antenna. Antenna means it's something absorb the right. So what this antenna does, it absorbs the sunlight energy, and then it funnel that energy to this P. So P is called photosynthesizer. It is also one type of chlorophyll molecule. So when I say plants have a chlorophyll, right? Plants have a not just one type of chlorophyll, but there are many different type of chlorophyll molecules present in plants. Okay, so these circles are one type of chlorophyll, and this P is another type of chlorophyll. Okay? So when this P gets energy from this antenna, right? So just in a simple example, right? If you give energy to something, it gets excited, right? So the molecule get excited, so it becomes star means get excited molecule. When it excited, so now this chlorophyll, what it does, transfer electron. It loses electron to the this A, which is the acceptor. Okay, so A is called electron acceptor. So the P loses electron to acceptor. In other words, the P is transferring electron to the A. Okay, when it does that, it creates this it's called a radical pair. Why we call radical? Because it has a one unpaired electron, so it has a it is defined as a radical, right? So when you have something unpaired electron, it's called radical. So it creates this radical pair. This is called cation radical because it's a positive charge, because it's a losing electron, right? Something is losing means it gets positive charge, and something gaining electron means it gets a negative charge, right? So you get this radical pair. And if you notice that these two radicals are next to each other, right? So they're very close to each other in a space. If they're close to each other, what happens? This electron, right, prefers to come back to the P, right? So it's called something called recombination. So the electron prefer to come back to the P. If that happens, right, basically, this entire system relaxes to the ground state. In other words, there will be no photosynthesis in plants. Okay, if the recombination happens, there will be no photosynthesis. Okay? So to avoid this waste process, what plants do, what they do, they, before the recombination, they introduces this extra molecule, which is called D, is called electron donor. The D means donor, right? It introduces donor. Now what this D does, so D transfer electron from itself to this cation radical, right? By doing so, now the D becomes positive radical, right? It becomes cation radical, and the P becomes neutral, and then A is as is anion radical, right? Now, if you compare this radical pair and this radical pair, right? So the second radical pair, so two radicals are slightly away from each other. Right? They are slightly away from each other compared to the first radical pair. Therefore, the second radical pair is slightly more stable than the first radical pair. Okay, so we measure this stability in terms of lifetimes, which means how long this radical pair survives. That is a very important step for photosynthesis. Okay, so this is a slightly more stable than this radical pair. So based on this simple design principle, what nature does, it introduces multiple donors from the left-hand side and multiple acceptors from the right-hand side. By doing so, it pushes these two radicals pair far from each other. Okay, and then eventually it creates one very stable radical pair, and its lifetime usually in microseconds. Okay. And the microsecond is actually, that lifetime is more than enough to do fundamental, like in nature's two fundamental reactions. One, oxidation of the water, right? Plants oxidize the water and produce the oxygen gas. So this is the oxygen gas we are breathing to survive, right? And the other side, it convert carbon dioxide into carbohydrates. Okay. So the efficiency of these two reactions, carbon dioxide to carbohydrate, water oxidation process, completely depends on the stability of this radical pair. Okay, so the higher the stability, so the higher the efficiency of these two reactions. Okay, so that's how natural photosynthesis operates. But remember that here something. Oops, what happened? Sorry, I think we did. Okay. All right. Can you see my screen now? Okay.
Yes, sir. Yes, sir.
Okay, thank you. Okay, just want to make sure that, okay. Yeah, so, the two actually, the operating principles here, one is something called energy transfer, the other one is called electron transfer. These are the two fundamental processes, operate in this entire process. So I want to actually introduce you what is meant by Am I audible?
Yes, sir. Yes.
Yeah, okay.
Yes, sir.
Okay, thank you. All right. So this is the natural photosynthesis, right? So now I'm going to actually show what is the artificial. So you can see that. So this is the artificial photosynthesis scheme, and you can see it's very similar to the natural photosynthesis. We have an antenna, and this is something called, again, the same thing, right? So we have the same thing here. So this is something called a reaction center. You can actually consider as a heart of the system. Okay. And so that is a reaction center. And then we have this, this side with something called, it's a reduction catalyst, and this side we have something called, oxidation catalyst, right? So the oxidation catalyst is going to oxidize the water to oxygen gas, okay, and it produces protons, right? And we collect these protons, and then supply pump these protons to this side of the system, right? Now we use those protons here, and then we combine with the electrons, then you can produce a hydrogen gas, right? The hydrogen gas is a fuel, right? So hydrogen gas is an example for the solar fuel. So this is how we can actually produce a hydrogen gas by using the sunlight energy. In other words, you're trapping your energy in the hydrogen molecule. Okay, and so if you look carefully actually here, so what actually exactly you're doing here, simply you're taking water, right? So you're taking water on the left hand side, you're extracting the 4 electrons from water, and you're pumping those electrons to this way, to this catalyst, and then you're combining those electrons with the protons and produce the hydrogen gas. So the net reaction is going to be 2 waters, and then the photon, which is the sunlight energy, and then you get a hydrogen gas and oxygen gas. So this is your solar fuel, right? You could do this chemistry for many other things. For example, instead of using proton, if you use a carbon dioxide, then you could actually convert into methanol or formic acid or formaldehyde. You could convert into different chemical energies. Okay, again, the same 2 operating principle, energy transfer, electron transfer, operate here. Okay, so let's quickly look at what is energy transfer means here. So energy transfer means, from the name you can actually guess. Energy transfer means, energy is transferred from one molecule to the other molecule. Okay, so the way it happens, so this is a D means again it's a donor is acceptor, right? So you're going to excite your donor with a light. When you shine a light, the molecule get excited, right? The donor get excited. These are the electron pair, right? You get excited, right? This is excited donor, and then excited, when it get excited, remember when you excite the molecule, the molecules are not stay forever in the excited state. After some time they're going to relax back to the ground state, right? When they does that, what they do, they release this extra energy in the form of photon, and now this photon is absorbed by the nearby acceptor. Okay, this is the acceptor, and then acceptor get excited. So what is happening here, you're providing energy to the donor, okay, and then donor is actually transferring its energy to the acceptor. So you're creating this the acceptor, the excited acceptor molecule. Okay, so this is kind of this is how energy transfer happens. There is this big equation, but you don't have to worry about that. Okay, so this is actually how happens right now. For example, you have this molecule here. It's called pyrene, and there is a porphyrin. They are connected to each other. When you excite the pyrene molecule, right? What are you going to do? What are you going to see? You're going to see the emission from the porphyrin molecule. Emission means you're going to see the fluorescence from the porphyrin molecule. So if you see that, that means you're going to have a energy transfer in your systems. Okay, so to have energy transfer, one of the fundamental requirement is that the donor fluorescence must overlap with the acceptor absorption. So this overlap is essential for energy transfer. If there is no overlap, means there is no energy transfer between the donor and acceptor molecule. Okay, that's the energy transfer. Okay, let's look at the electron transfer. So I'm going to show 2 types of electron transfer here. Again, you have a donor molecule here. You get excited, right? The excited donor. In excited state, what it does, instead of transferring energy, it transfer electron. So it transfer its electron to the acceptor, right? And then it create this cation radical and anion radical. So it creates this radical pair. Okay, so this is something called oxidative electron transfer. In oxidative electron transfer, you excite the donor molecule. Okay, And then if you take another type of electron transfer, which is called reductive electron transfer. So here, instead of exciting the donor molecule, you can excite the acceptor molecule, A molecule, get excited, right? Now, here, electron is going to transfer from here to here. Then you're going to create the same radical pair, but in a different pathway. So this is called reductive electron transfer. So I'm going to use this, three different, processes: energy transfer, oxidative electron transfer, and reductive electron transfer to characterize the molecules I'm going to show in the next slides. Right. So okay, now we know those are the two processes. Now I'm going to show. So again, this is what actually our target is. We want to design the system, but as you can see, it's multi-component system. Means there are a lot of things actually, a lot of molecular component present in this, right? So in order to produce solar fuels, what you have to do, you have to somehow assemble this all these molecular components, make them to work together to produce the solar fuels, which is a challenging system. Therefore, what we're doing, we are going step by step. So initially, we are trying to mimic this, we call reaction center. Okay. So the idea is that we want to do this. We want to create this radical pair with long lifetime. In other words, with a high stability. Okay. Higher stability means longer lifetime. Okay. Because as I said, so the lifetime is directly depends on the efficiency. I mean, the lifetime of this radical pair directly affect the efficiency of the this reaction as well as this reaction. Okay. So anyway, so this is what we want to design, right? So we want to design this reaction center. We need a sensitizer. So what we did, we chose aluminum porphyrins, right? If you remember, I showed you first series, that's aluminum porphyrin. It has this carboxyl group, right? It can react with hydroxy group. It can react with this carboxyl group, carboxylic acids or alcohols. And also, it can make a complex with Lewis bases. So what we did here, we're going to use these two reactive bonds to design this reaction center. Okay, so yeah, we have aluminum porphyrin here, and as an electron donor, we chose these particular molecules. Okay. And as an electron acceptor, so we chose the fullerene molecule, and also sometimes we use nanoparticles. Okay. Right, I'm going to skip all these things. Okay, so these are the some systems we designed by using this design principle. There is aluminum porphyrin, that's a P, that's your P, and this is represents your D molecule or electron donor, and this represents your acceptor, right? So we publish a lot of such examples. I'm not going to discuss everything here, but I just want to quickly talk about this recent result. I'm going to show how we design this, synthesize this molecule, and how we characterize it. But again, remember that in my lab, we do a lot of synthesis. Okay, so we always start with from scratch from the precursor molecule. So you take a C16, and you do this reaction. You can get this molecule, so which has a carboxylic group. So this is the carboxylic we're going to use to connect to the porphyrin. Okay, and then if you react these two molecules, you're going to get this this molecule. Now we're going to use this as the electron donor, and this is the electron acceptor. So once you have that, so you're going to start with aluminum hydroxyporphyrin, right? So as I said, this is the very reactive functional group. You're going to react with the carboxylic acid. You can connect the fullerene, right? You got the something called diode. Diode means it has a two molecular components, 1 and the 2. Once you have this diode molecule, then you can construct this triad. Now it has a 3 molecular components, so 1, 2, and 3, right? And just note that here R is the these 3 different substitutions. So once we, complete the synthesis, we, use the different spectroscopic methods to make sure that we really got this molecule. Right? This is just NMR to show that, we have this, we have this molecule. Okay, so what we want to actually show here, we want to do, remember, we want to transfer electron, from there to here, right? And then after that, we want to transfer the second electron from there to there. This is what actually we want to do, right? But how to characterize this electron transfer? Well, there is something, method called transient absorption spectroscopy. It's very similar like a, absorption spectroscopy. Probably maybe you're using in your undergraduate laboratory. Okay. So, what you do here, you take a molecule, right? You excite the molecule with something called pump laser. Laser means light. You excite the molecule, molecule get excited, and then when it is in excited state, you're gonna watch this molecule with another light, which is called probe laser, right? So the probe laser will watch this molecule, and it precisely, tells whether this molecule is what this molecule is doing, whether it is doing energy transfer, or it is doing electron transfer, or it is doing something else, right? We can precisely monitor by using this probe laser, right? Something called, transient absorption spectroscopy. So let's say that if you do electron transfer, right? So if you transfer electron from porphyrin to C60, right? We know that we are creating radicals, right? And these are some of the radicals should form when you do the electron transfer. And each of these radical has its unique absorption profiles. They have very, specific absorption positions, right? So from your data, if you see these absorption profiles or specific absorption, you can tell whether, you're creating these radicals or not. If you're creating these radicals, that means you're doing electron transfer. So that's how this technique works, okay? Okay, here is the, very busy slide, but I just want to show that, let's say, you have this molecule, right? You are exciting porphyrin, and you're transferring electron from, aluminum porphyrin to the fullerene, right? And, you're going to make a fullerene anion radical, okay? And, as you can see, the fullerene anion radical has a, specific absorption profile, means, it absorbs the light around 1000 nanometers, right? And you can see this is the, spectrum you get from this, technique. And you can, in this spectrum, there are a lot of, absorption profiles. But if you look at carefully around 1000 nanometers, there is this, broad absorption band, right? So the presence of this band indicates that, yes, in fact, we are, creating the fullerene anion radical. Okay? That means indirectly telling it tells that we are doing electron transfer from aluminum to the C60 molecule. Okay. Not only that, so now what we can do, we can monitor the absorption as a function of time. Okay. You watch the absorption with the time. Is it decreasing or is it increasing? By monitoring this absorption, you can actually precisely calculate, electron transfer lifetime. Okay. So those are actually, represent this decay curves here, right? So the blue one actually corresponds to the the red one actually corresponds to this one, right? So this is the time scale, and that's your absorption change. And now what we did, we have a diode, then add the another molecule, make a triad, right? So we know that we have electron transfer from here to here. Now let's make sure that we have electron transfer from there to there, right? And if you do electron transfer, it will also create a this radical pair, and this radical pair, if you compare this radical pair, so we have a C60, still we have C60, right? So which means still this exists, and most importantly, these two radicals are slightly further away compared to this one, which means technically this radical pair should it should be more stable than this one, right? So you can actually you can see that from this decay curves. So the blue one actually corresponds to the the lifetime, the C60 or this this band absorption as a function of time. You can see that both are kind of following the same timeline, right? But you can see that almost like a this longer time scale is slightly different, right? But if you go for when R is this one, now you can clearly see that they are very different, right? Blue is actually much kind of slower than the red one, and here blue is much slower than the red one, right? So these results clearly indicates that we are doing electron transfer, or we are creating this radical pair. Moreover, we are stabilizing this radical pair compared to this radical pair, exactly like what nature does in photosynthesis. And if you look at the, if you summarize those results, right? So if you excite the porphyrin, you're doing electron transfer, and that lifetime is, you're doing electron transfer within 152 picoseconds. Okay? And then radical pair survives up to 39 nanoseconds. And then you introduce this molecule, then you're going to do this second electron transfer. And then, this radical pair survives now 56 nanoseconds. You can clearly see that we are stabilizing. In other words, we are increasing the lifetime of the radical pair. And if you summarize all the all the systems, we initially got a 39 nanoseconds, right? It becomes 56 by adding the this molecule, and if you keep going on that, so we actually stabilize 39 nanoseconds to 1240 nanoseconds. This is extremely stable radical pair, and such a stability actually is going to be very important for designing the artificial photosynthetic systems. Okay. All right, that's one example. And now actually I want to show something. How much time I have? Do I have enough time? How much time I have still?
Sir, continue, sir. No problem, sir.
Oh, no. Okay. All right. So, I think I hear my.
Hello.
Okay. I think I'm hearing my echo.
Hello, sir.
I'm hearing my echo. Can you please I think mute your.
Okay, sir. Okay, sir.
Yeah, thank you. I'm still hearing my echo. All right. Okay, yeah, now good. Okay. Yeah, so the next example I'm going to show. So, in the first example, I showed you how to, build this reaction center, right? Now I'm actually going to show how to couple this one with, this side of the, water oxidation process. It's actually, if you, this basically this assembly, mimics the something called photocatalytic cell. In other words, kind of a battery, right? So we have an anode this side, we have a cathode. Okay, so this is something called photocatalytic cell. So what we do here, so we have an anode, but this anode is called photoanode, which means it's a photoactive. Okay, so you have an anode, right? It's kind of a glass plate. Okay, on top of that, what we do, we put a semiconductor, semiconductor nanoparticles, either titanium oxide or tin oxide. Okay, and then on top of that, you're going to have your sensitizer, porphyrin molecule, and then on top of that, you have a catalyst. Okay, so when you shine a light on the this P sensitizer, what it does, it transfers electron to this conduction, semiconductor. And then the sensitizer loses electron, right? And then, what it does after losing that electron, it regains that lost electron from the catalyst. Okay. And then, the sensitizer becomes neutral, but one electron is going to be, end up in the semiconductor. So that electron actually travels, to anode, and it will travel this way, and it will go to the cathode, right? Now you have a, electron here, right? And then, this process continue up to 4 cycles, like, first photon, second photon, third photon, and fourth photon, right? So fourth photon means, sensitizer is going to inject 4 electrons here, and then catalyst is going to lose the 4 electrons. When catalyst loses 4 electrons, it's going to go for water oxidation, and it breaks the, water into oxygen gas and protons. Okay. So those 4 electrons actually collected here. So I have 4 electrons here, and then you have protons. So electrons and protons are combined. You can produce a hydrogen gas again. Okay. So this is something called, photo catalytic cell or photoelectrochemical cell. So here, what we are doing, we are converting sunlight energy into chemical energy. Okay. So that exactly, what this side of the system does. Okay. Now, I also want to show that, if you, simply, remove the catalyst, right? If you remove the catalyst, right, it becomes, solar cell. It's something called dye-sensitized solar cell. And, again, it's the same principle, right? So you inject electron, those electrons actually, travels this time through this bulb, basically, right? So the difference between the catalytic cell and this dye-sensitive solar cell, that, here you are producing, chemical energy. So sunlight energy is converted into chemical energy, but here sunlight energy is converted into electricity. Okay, but the idea is that, you're converting sunlight energy into some useful form of energy. So this is, something actually we work on in my lab. So these are some solar cells you can see. This is the one solar cell, and you can see there are some connections here, right? And one of my students actually made this solar powered calculator. I mean, most of our calculators are solar powered, but what he did, he removed the solar panels from the calculator, and he replaced them with this these solar panels, right? So now just operate like normally. Okay. So how do we design these cells? Well, to design these solar cells, the energetics has to match. Means, remember that. So the sensitizer, right? This sensitizer should be higher in energy. Then only you can inject electron into semiconductor. Okay. And the catalyst also must be higher in energy than this state. So we have to maintain this energy state, in a way that these two processes can operate in the system. So these are some examples, and I'm showing here. So we build this, there is a semiconductor here, right? And this is the glass plate and semiconductor, and there is a sensitizer, and this is the kind of a catalyst we have. So we showed that you can transfer electron into semiconductor, and you could use this setting as a photo anode for either photo electrochemical cells or solar cells. Okay, I think I'm gonna skip that. All right, that's the artificial photosynthesis. I'm gonna next jump on to the second project, which is light-induced molecular machines or molecular electronics. Okay, so this is something slightly different. If you recall a 2017 Nobel Prize in chemistry, so the 2017 Nobel Prize was actually awarded for this the molecular machine work. Dr. Fraser Stoddard from Northwestern University. Okay. But anyway, so what we're doing here, it's a simple design principle. We have two porphyrins, right, either side. And then we connect these two porphyrins with, this kind of bridge, right? So this rectangle thing is a one molecule, and these two rectangle things also another molecule. Okay, and then this, this cyclic thing also one type of molecule, right? So the idea is that when you shine the light on the porphyrin, right? This porphyrin, for example, we talked about antimony porphyrin and phosphorus porphyrin, right? And I showed that their reduction potentials are very small. Means if you use a phosphorus porphyrin or antimony here, they accept electron, right? They easily accept, right? So they accept electron. So the electron transfer from here to here. And when that happens, this molecule gets the positive charge, right? When it loses electron, you get a positive charge. So when you have a positive charge, so this positive charge, right? So this positive charge and these positive charges, repel each other. Just kind of electrostatic repulsion, right? So the same charges repel each other, the opposite charges attract each other, right? So initially, when there is no charge, so this ring prefers to station on this molecule, okay? But when there is a positive charge, then the positive repel each other. So those repulsions causes repulsion push this this molecule to this molecule. Now you're going to see this one. Okay. So when you shine a light, electron transfer happens here, and then this molecule move here, right? That is going to see here. And then when you stop a light, if you just stop a light, and then the electron actually it goes back to here, and then it neutralizes. When it neutralizes, this again cyclic molecule prefers to come back here, right? So the idea is that by just using the light, so we want to move this molecule back and forth between let's say we have this shuttle buses, right, between the two towns, right? This bus actually shuttles between these two towns, right? Same way, if you assume this is a bus, right, and then this can actually shuttle between these two stations by using light. To shine a light, shine a light, this will go there, and then stop the light, it's going to come back. So the light energy is converted into mechanical energy here. So that's actually the design principle for these machines. Okay, so what exactly these machines are useful for? Well, I think nowadays we are using, everybody has a mobile phones, laptops, iPads, everything, right? As you know that all our electronics actually has a electronic component inside, okay? And all of these electronic components work on the binary system, which is called a 0-1 system, right? Now, you can actually define those 0-1 binary systems here, right? So let's say if you define this state as a 0, right, this state is going to be 1, right? You can actually go back and forth between 0-1 state by using external factor, such as light, right? If you can create such ability in your molecule, those molecules is going to be useful for these electronic devices, especially for memory storage devices. Okay, so that's one application these molecules have, and also they are actually useful for drug delivery systems. For example, here, right? So you have this this kind of a spherical object, right? It's a silicon nanoparticle, and you can see there is a holes right on the nanoparticles, and on the top of the hole, these machines are embedded, right? You can see in a close up here, right? So that's a hole of the this hole, right? And then this is the the nano machine, just like similar to this one, right? So there are station 1, station 2, and this is the cyclic molecule, and these are the stopper. Stopper means basically these are actually called stoppers. Means they keep the they kind of keep this molecule on this axle. Otherwise, this can escape from the axle, right? It's called a kind of stopper. So you have a stopper and the 2 stations, and you have a the cyclic molecule, right? So what you could do, you fill your drug inside this cavity. You put your drug inside, okay, and then give this nanoparticles to the patient, right? And then this nanoparticle is going to be distributed in the body. After certain when you see that these nanoparticles are localized on certain specific area in the body, okay, now you want to deliver your drug, right? What you could do, you apply some external potential. When you do that, this cyclic molecule is going to move from this station to this station, right? It can move here. So basically, when it is here, it's kind of a cap. It kind of act like a cap, so the drug cannot escape, right? But when it moves here, so the drug, is kind of, you're opening up the cap, and then drug can escape. Means you're delivering the drug at at specific location in the body. Okay, so this is the another application for these systems. So that's one design, one way you can deliver. Another in another ways that one, let's say you have same cavity. There is a drug in the cavity, and you have this machine, but this time you have only one station. So here, instead of moving this cyclic molecule, you're going to snap it. Means basically you're going to break the chemical bond. So this will fall apart, right? So this will stop, will go away, and this will escape, and then you're opening up the cap, and then drug will be delivered. Right? So this is the the operating principle of the drug delivery system. Okay, so what we do in lab, so these are the components we have chosen to design these machines. So we have 2 stoppers here. So this is a cyclic molecule. So these are the 2 stations, and this is the just connecting bridge between molecules. Right, this is the molecule we designed. Right, you can see there is 2 molecules, and this is a cyclic molecule. That's a station 1 and the station 2. The idea is that if you shine light, you want to move this molecule from here to here, right? That's the idea. But again, if you want to design the system, it's not easy to do in one single step. Okay, so what we have to do, again, we have to go step by step. So what we're doing, we are monitoring this part of the system. Okay, we wanted to make sure that the phosphorus porphyrin is going to accept electron from here, and then also this naphthalene is going to make a complex with this cyclic system. So that's what actually we were monitoring at the initial point. So these are the systems we prepared. You can see there is a phosphorus porphyrin, right, in naphthalene, and we use a different bridge length between naphthalene and porphyrin to optimize the conditions for this application, right? And also we use a different porphyrin. Okay? And all these porphyrins, when you excite these porphyrins, right? Okay, this is the synthesis scheme. Again, you can start with this porphyrin, insert the phosphorus, and then you can attach your these groups. Okay. Okay, so this is the fluorescence study. So what fluorescence studies tell us here? It will tell us that whether we have a electron transfer or not, right? So if you remember, we needed this electron transfer, right? We need electrons. If you excite the molecule, we need an electron transfer from here to here, right? So that's what actually we are monitoring by using
planetary motion. And విశ్వంలో తిరుగుతూ ఉంటే the planets and revolve around the sun అని.
Okay, just monitoring that, right? So you can see that this is the reference compound, means there is no naphthalene, and this is the the studied compound with the naphthalene, right? There is a big difference in the fluorescence, right? So the difference in the fluorescence clearly indicates that we have an electron transfer in these molecules, but not all of them. Some of them have electron transfer. This has electron transfer. This has a small amount of electron transfer. This has almost none, right? And these 3 porphyrins have a very strong electron transfer, right? So one thing we know that we have electron transfer now, okay? And the second objective is that whether this can make it complex or not, right? So the naphthalene is going to make complex with this one or not, right? So what we did here, we take this molecule. It's initially is a colorless compound. Okay, so if you dissolve in a solvent, it's a colorless compound. and then add this one to this compound, right? Is it immediately becomes this orange color. Okay, so which indicates that basically this naphthalene is actually inserted into this ring, something like this, and it is making this complex. Okay, so that's a good news, right? And then also we added this one. Now this has actually this has only one arm, but this has a two arms, like two sides, right? So again, it makes it complex. And what we found out that this has a better complexation with this one compared to this one because this extra arm. Okay, so now we know that we have electron transfer. Okay, and also we have a complexation. So we basically what we proved here, we successfully optimize the conditions for this part of the system. So currently, we are actually working on the other part of basically the entire part of the system. We constructed this the axle, and we are monitoring the mechanical movement of this molecule within this system. And that's the molecular machines. I'll skip these slides. Okay, so this is the last one. So as I said, this is a photodynamic therapy. It's it's entirely different from the first two projects, and it's for treating cancers basically. So you have a let's say how this works. This is this is how it works. This is a let's say cancer patient, right? You're gonna inject your drug. Drug means again we are using porphyrin molecule here. So the drug is going to be distributed in the body. You have a normal tissue and also you have a cancer tissue. And the way we design this drug molecule, they selectively binds to the the tumor tissue than the normal tissue. Okay, they're gonna bind to the cancer cell, and then you're gonna shine a light on them, right? When you shine a light, they're gonna generate a one toxic species, and that toxic species is gonna kill the cancer cell. Okay, so this is a mechanism. So what happens if you shine a light on the PS? So your photosensitizer excited, right? Star, and then it go to the one means singlet excited state. Okay, and this singlet excited state undergo intersystem crossing to the triplet excited state. And then when it is triplet excited state, right? So we know that cells have a oxygen inside, right? So the oxygen that we breathe is a triplet oxygen. So this triplet sensitizer interact with the triplet oxygen, and then it transfer its energy to the triplet oxygen. It convert into singlet oxygen. So this singlet oxygen is a highly reactive species, or toxic, you can say. And this is the one actually responsible for killing the cell. So killing means basically this is gonna indiscriminately react with the biomolecules in the cell. That's how the cell is gonna be destroyed. Okay, so that's the kind of operating principle. And this is the Jablonski diagram. You can see kind of a same thing in the same mechanism, but I'm showing that in a pictorial way. You excite your molecule, right? It goes here, and then from there, it undergoes this intersystem crossing. It gets this triplet state, okay? And then in triplet state, it interacts with the triplet oxygen. So it transfers that energy, right? It goes to the ground state, and it transfers that energy to this one, and this one excited, and this is the reactive species, and it reacts with the biomolecules, and it kills the cancer cell. Okay. All right, so what we're doing here actually, we just, I'm not actually showing, the data, but just kind of a couple examples here. We tested the, what do you call, the cytotoxicity of these three porphyrins. There's a phosphorus porphyrin, right, which is the, 3 phenols, 1 pyridyl, and this is phosphorus porphyrin with methoxy, and this is the antimony porphyrin, right? And this is the reference porphyrins. It's kind of common reference porphyrin in the field. So when you see this IC50 means, basically what is the concentration is required to kill the 50% of the cells. Okay, so the smaller the value is better the efficiency, that means. Okay? So what is that means? With the blue light, we are using actually blue light to what we do here. We take a cells and we add these porphyrins. Okay, we incubate. Then we measure the the cytotoxicity in dark as well as in the light. Okay, we want to see what is the their efficiency in the dark and what is their efficiency in the light, right? Because remember, so the PDT means you need a light, right? So we want to make sure that there is a the effect of light. So when we do our study, this is kind of a light source, so red light. So, but in this case, in a blue light, so it's only 40% increase means dark and the light. So if you shine a light, the cytotoxicity or toxicity increases 40% for this one. Okay, this is a standard one. And then these two samples are actually our own samples we prepared in our lab. And when you look at this guy, you can see that it's almost like 290% increment in which is cytotoxicity from dark to light conditions. Okay, and this is also almost like 250, and you can see that these two porphyrins actually shows high cytotoxicity, okay, in presence of light, which means they are showing a very strong PDT results on the cancer cells. Okay, so that's, I think, last slide. And I want to quickly summarize here. I think I hope that I introduced the porphyrin chemistry and I introduced what is porphyrin and the properties and how we can use these properties for different applications. Okay, especially we could use them for production of solar fuels. We could use them for construction of molecular machines. Also, we could use them for curing the cancers. Okay? And I would like to thank you all for your kind attention. And I just want to mention that where we are located, we are this is the these are the 5 Great Lakes, right? So this is the Lake Superior. And we are actually located at the tip of the Lake Superior, which is the town called Duluth. Okay, and you can see this is the Lake Superior, and this picture I took it from one of the hills in the town, and yeah, so this is we are kind of a we call central, mid-central US. Well, anyway, thank you very much for inviting me again and giving me this opportunity, and also for your kind attention. I would be happy to take any questions if you have any. Thank you.
Thank you, sir, for your outstanding presentation on main group porphyrin properties and series of porphyrin.
Thank you.
Solar fuels, light-induced molecular electrons, etc. We are grateful for the time and the effort you took to share your knowledge and thoughts with us, sir. Thank you very much, sir.
Thank you.
Dear participants, please type your questions in the chat box now.
Excellent presentation, ma'am.
Oh, thank you. Thank you.
Explained well. Every aspect is covered. Explicit presentation.
Oh, thank you. Thank you.
Best wishes to you. I am Sushil Rao from Krishna University.
Oh, okay. Hi. How are you?
Yes, sir. I'm a retired police officer, elderly man.
Okay.
Due to passion, I am studying this research.
That's great. That's great. Great.
Best wishes to you, sir, again, once again.
Yeah, thank you. Thank you very much.
Hope there is no further question. We will proceed to the last session of the day.
Okay. All right. Thank you, everyone.
Now I request Mr. D. Srujana Devi, lecturer in Department of Botany, to propose the vote of thanks.
Thank you, Anuja. It's my privilege to propose the vote of thanks for this second day of 5-day international webinar. Respected corresponding, principal, colleagues, our most valued resource person of the day, Dr. Prashant K. Podduturi sir, and dear participants. On behalf of the entire fraternity of JMJ College, Tenali, it has been such an honor to be a part of this wonderful event. On behalf of the organization, I would like to express my heartfelt gratitude to all esteemed delegates of the webinar for their presence and contribution to make this webinar a great success. At first, I extend my gratitude to our Honorable Speaker of the Day, Dr. Prashant K. Podduturi sir, to take out time from his busy schedule to grace the event and sharing her valuable thoughts and methods. Thank you, sir, for your interesting and highly informative session of the day. I express my deep gratitude to our correspondent, Dr. Sister Teresa Magade, for supporting us to organize this webinar. I express my sincere thanks and special regards to our beloved principal, Dr. Sister Shiny KP, for giving us all the guidance and help to conduct the webinar for the good of community at large. I would like to thank our beloved Vice Principal, Sister Sharada Mary, and Dr. V. Sumalata, the coordinator and convener of International Webinar, for their support and assistance. My sincere thanks to all the members who participated in the webinar and made it a grand success. Thank you, one and all. We shall meet tomorrow at 10 o'clock. Thank you. Thank you, sir.
Sir, thank you so much, sir.
Thank you. Thank
So
you.
tomorrow is 10.
Thank you.
Yes, sir. Tomorrow is 10 o'clock.
Thank you, sir. Very informative.
Confirmed. 10 o'clock. 10 o'clock.
Yes, sir. Yes, sir.
Yes, sir. Tomorrow meeting is successful.
ఆయన ఉండాలి మేడం. ఆయన సాటర్డే దాకా కంటిన్యూ అవ్వాలి.